Students, in this note set, we're going to take a look at some of the more advanced features of Lewis structures. Here's where it starts to get really interesting. We can use Lewis structures to represent ions, polyatomic ions, so many atoms all put together. When we do this, it's two simple rules. If the polyatomic ion has a negative charge, which is very often the case, more often than not, a polyatomic ion has a negative charge. In that case, you would add electrons to the total count of valence electrons. You would add a number of electrons equal to the magnitude of the charge of that ion. If the ion has a positive charge, instead of adding electrons, we're going to subtract electrons. Now, remember that electrons are themselves negatively charged particles. So adding an electron to the number of total valence electrons means you're adding one more unit of negative charge than you had before. And if you're subtracting one of those negatively charged electrons, then you're giving a charge that for the ion that is 1 unit higher than what it would be otherwise. One last thing about drawing Lewis structures for polyatomic ions, it is technically proper, once you've written a good Lewis structure, to put large brackets around your entire drawing and then write the ion's charge outside the brackets. We'll see how this fleshes out in just a second. Let's say we're asked to draw a Lewis structure for the phosphate ion, PO4 3-. Let's start like we've done for every Lewis structure thus far. We'll give dot diagrams for every atom that we see in that ion. So there's 1 phosphorus and there's 4 oxygens. Let's just draw dot diagrams for those atoms. Phosphorus you can find in group 15, just below nitrogen. And then oxygen, of course, is at the top of group 16. And there's 4 of them. So we've got to draw 4 dot diagrams, 1 for each of the oxygen atoms. All right, let's add up the total number of valence electrons. And remember that there's a 3- charge. So after adding up the number of valence electrons for phosphorus and then 4 times the number of valence electrons for oxygen, add a bonus 3 electrons because it's a -3 charge. So 5 from phosphorus, 6 from each of 4 oxygen atoms, and then a bonus 3 due to the -3 charge. That gives us a total of 32 valence electrons for the phosphate ion. Okay, let's connect the central atom to the satellite oxygen atoms with single bonds to begin with. So central phosphorus, 4 single bonds used up or made at first. We'll subtract double the number of single bonds from the total of 32. So 32 total valence electrons minus the 8 used in single bonds gives us 24 remaining electrons. We will try to satisfy the octet rule with those 24 remaining electrons. Now, notice that the central phosphorus atom already has access to 8 electrons, so it doesn't need any additional dots. But the oxygen atoms sure do. Let's put 6 around each of the oxygen atoms. That'll use up 24 dots. And then lastly, this is just a formatting issue. If it's a polyatomic ion, like we have here, put brackets around the whole structure and then write the charge outside the brackets. So slap large brackets, in this case, around the whole structure and then put 3- outside of it. Let's try this for a positive polyatomic ion. Let's try ammonium, NH4+. We'll start like we do for any Lewis structure problem. Draw dot diagrams for each atom. So nitrogen, column 15, 5 valence electrons. Hydrogen, of course, column 1, 1 valence electron. There's 4 of them, so you've got to draw 4 dot diagrams, 1 for each hydrogen atom. Okay, now when we do the total count of valence electrons, here we have a +1 charge. So we're going to add up 5 from nitrogen, plus 1, plus 1, plus 1, plus 1 for the hydrogens. And then from that total, we'll subtract 1. So 5 from nitrogen, 1 from each of 4 hydrogens, and 1 less because we have a positive charge. So 5 plus 4 minus 1, that's 8. 8 total valence electrons. We'll connect the central atom to the satellite atoms with single bonds at first. So the central atom is the one that we only have 1 atom of, nitrogen. Connect hydrogens with single bonds. Aha! Those 4 single bonds used up all of our valence electrons. We had 8 total valence electrons. In order to make 4 single bonds, we used up all 8. That means we have 0 remaining electrons. Did we satisfy the octet rule for nitrogen? Well, yeah. 4 single bonds around the nitrogen, that means it has access to 8 electrons. And then for hydrogen, it's the duet rule. Does each of the 4 hydrogen atoms have access to 2 electrons? Yeah, a single bond is a shared pair of electrons. So we've got a good Lewis structure here. No further dots needed. One last formatting issue. Since we've got a polyatomic ion, slap brackets around the whole structure. These are going to be quite large brackets. And then write the charge outside the brackets. So it looks like this. A charge +1 outside large brackets. Okay, let's try some fun ones now. Okay, we've got polyatomic ions. What if I ask you to draw a Lewis structure for sulfur hexafluoride, SF6? Start like you would any Lewis structure problem. Dot diagrams for every atom. Okay, fair enough. We've got 1 sulfur. Sulfur is group 16, right below oxygen. 6 valence electrons. Fluorine at the top of group 17. 7 valence electrons. And SF6, that means there's 6 fluorine atoms. Yikes. Okay, a little bit of math here. Each of the 6 fluorine atoms contributes 7 valence electrons. And then we're going to add another 6 from the sulfur. That gives us a total number of valence electrons of 48. Yeah, that's a lot of valence electrons, isn't it? Okay, we're going to keep following our procedure. We'll connect the central sulfur atom to each of the 6 satellite fluorine atoms with single bonds. 6, wait, 6? Yeah, 6, because it's SF6, 6. Holy cow! Aren't we violating the octet rule? Look at how many electrons are around sulfur. 2, 4, 6, 8, 10, 12. The central sulfur atom has 12 electrons around, and we haven't even bothered to place extra dots yet. We're way over 8 here. Are you feeling uncomfortable? Students, check this out. Rules are made to be broken. Look at this. Here's your rules. Ripping it. Sometimes we do need to break the octet rule, but it's only under certain circumstances. So, students, there's rules about breaking the rule. Okay, when we need to break the octet rule, the violating atom, the one that has more than 8 electrons around it, number 1, it must be the central atom in the Lewis structure. Okay, it can't be in SF6. It could not be one of the fluorine atoms because it's not. Fluorine was not the central atom. Only the central sulfur atom was eligible to break the octet rule. And then secondly, the violating atom, regardless of whether it's a central atom or a satellite atom in a structure, it may not be in the top 2 rows of the periodic table. We call those periods 1 and 2. So the hydrogen helium period, that's period 1. And the lithium on over to neon row, that's period 2. Any of those elements may not, under any circumstances, break the octet rule. Okay, let's go back to SF6. Yes, we're breaking the octet rule. Is our violating atom, the sulfur atom, is it the central atom? Yes. Is the violating atom in the top two rows of the periodic table? Check sulfur's position on the periodic table. It's in row 3, period 3. So no, it's not. So sulfur is indeed eligible to break the octet rule. It's totally fine. Okay, once again, our total valence electron count was 48. In order to make 6 single bonds, we used 12 valence electrons. That gives us 36 electrons remaining. Can we place those 36 electrons around the satellite fluorines so as to satisfy octet rule for them? Because remember, if it's not a central atom, you've got to satisfy octet rule. You've got to follow it. Well, yeah, it works out perfectly. 6 fluorine atoms, each of which needs 6 more electrons, 6 dots around them, gives us this structure. Perfect. It uses up all of the remaining electrons. We're in good shape here. Let's try a sample problem. Draw the Lewis structure for PCl5, phosphorus pentachloride. I'll give you a second. Remember, draw dot diagrams for all of the atoms. Start there. We need this basic structure, central phosphorus with 5 single bonds to the chlorine atoms. We have a total number of valence electrons of 40, 7 from each of the 5 chlorine atoms, plus another 5 from phosphorus. If we're making 5 single bonds, that uses up 10 of the 40 total valence electrons. That gives us 30 electrons remaining. Okay. We were cool to break the octet rule here because, number one, the phosphorus atom is the central atom in the Lewis structure. So it's okay to have more than 8 electrons around the phosphorus. And the other reason why that's okay is phosphorus is not in the top 2 rows of the periodic table. It's in row 3. Period 3 is where you find phosphorus. Okay, now the chlorine atoms. You might say, hey, chlorine's in period 3. Can it violate the octet rule? No, chlorine is not the central atom. So we must follow octet for the chlorine atoms. We have 30 electrons remaining. If we distribute those 30 remaining electrons evenly among the 5 chlorine atoms, that gives 6 dots for each one. And as it turns out, that's a perfect structure. The chlorine atoms all follow the octet rule. Okay, so thus far we've talked about Lewis structures for polyatomic ions, Lewis structures that violate the octet rule. Now we're going to talk about another really fun type of Lewis structure, double and triple bonds. Let's start with this one. Draw for us a Lewis structure for oxygen molecule, O2. As with any Lewis structure problem, we'll start by drawing dot diagrams for every atom in the structure. So here we have 2 oxygen atoms. Each dot diagram has 6 valence electrons around it. That's what you would expect for group 16 elements. All right. Find the total number of valence electrons. This time it's very simple. 6 plus 6, that's 12. We'll start by making a single bond between the oxygen atoms. So since there's 2 oxygen atoms, there's no central atom here, so you can't have a center between 2 things. We'll subtract from the total number of valence electrons 2 times the number of single bonds. Well, there's only 1 single bond here. So 12 total valence electrons minus 2 electrons used in that single bond gives us 10 remaining. Okay, if we were to place the 10 remaining electrons around each of the oxygen atoms, you could put 5 around each. You still don't follow the octet rule. Now, a couple of things, students. A, there's no central atom in this structure, so nothing's eligible to break the octet rule. And then secondly, oxygen is in period 2, so it would not be eligible to break octet even if it were the central atom. And thirdly, when we break the octet rule thus far, we've seen atoms that have more than 8 electrons. Here, each of the oxygen atoms has fewer than 8. If we count the dots together, 1, 2, 3, 4, 5, and then in the bond you get 2 more. That gives 7. And it's a symmetrical molecule, so the other oxygen would follow the same thing. 1, 2, 3, 4, 5, and then 2 more from the bond, 7. Both oxygen atoms are electron deficient. They don't have enough electrons. So here's your question. How can we increase electron ownership while keeping the same number of total valence electrons? In other words, you can't manufacture an electron out of nothing. You can't just willy-nilly add an extra dot and call it a day, because then you're not following the correct number of total valence electrons. Okay, so let's try a double bond. To make the double bond, we're going to show each atom contributing one of its lone electrons, one of the dots that are not currently being shared, but we're going to contribute it to the sharing pool of electrons. So initially we drew a structure with a single bond with 2 electrons being shared. Now we're saying, what if each of the oxygen atoms contributed another shared electron? In that case, we now have 4 shared electrons. But each of the atoms in the structure still retains 4 unshared electrons. So let's look at the oxygen on the right. It's going to contribute one of its 5 dots, but it still retains this dot number 1, this dot number 2, 3, 4 dots of its own. If we redraw the structure, now we're going to draw 4 shared electrons. That means 2 bonds, or since it's between the same 2 atoms, we call that a double bond. So 2 bonds between the same atoms is a double bond. And check this out, students. Now the octet rule is satisfied. Each of the 2 oxygen atoms has 4 dots of their own, plus 4 shared electrons. 4 plus 4 is 8. Octet rule is satisfied. And we still haven't violated the total number of valence electrons, which has to be 12. I'll give you a second to try drawing a Lewis structure for N2. Go ahead and pause the video and come back when you're ready. In N2, when you draw a dot diagram for each of the nitrogen atoms, you would have 5 valence electrons. And since there's 2 of them, 2 times 5 is 10. So our total number of valence electrons is 10. Your initial structure would show a single bond connecting the 2 nitrogen atoms. So that consumes 2 of the total 10, giving us 8 electrons remaining. Okay, so at first you would have a single bond connecting 2 nitrogen atoms. The 8 remaining electrons you might divide evenly among the 2 nitrogen atoms, giving them 4 dots apiece. But hey, that doesn't satisfy octet rule. We've got to satisfy octet rule, number 1, because there's no central atom in a structure where there's only 2 atoms. And secondly, nitrogen is in period 2. It's not in period 3. We've got to satisfy the octet rule through multiple bonding. In other words, we need to further increase electron ownership by not break the octet rule, and also not just willy-nilly add more valence electrons, which is a common thing that students do. You can't just add more dots because you feel like it. In this case, both nitrogen atoms need to share 2 more electrons. If they each share 2 more electrons beyond the single bond that you might have initially drawn your structure for, you now have 6 shared electrons for each nitrogen atom, and each nitrogen atom also retains 2 of its own, a lone pair of electrons. So if you count up the total number of valence electrons for each nitrogen, it's 1, 2, plus the 6 electrons being shared in the middle, that equals 8. 8 electrons are needed to satisfy the octet. Beautiful.